Okay, Mr. Kelly, this is 1977, the practice AP exam that I missed. So you selected 25, 26, and 28 for me to do. I will have you know that this is the first day of my summer vacation, and this is what I'm doing. So in A, it asks you for work. Work equals force times displacement. It gave you forces negative kV, so work equals negative kVd. B asks you acceleration of the block in terms of kV and m. So if force equals ma, so negative kV equals ma, divide by m to get a, you get negative kV over m. C asks you for velocity of the block as a function of time, so you do an integral. V equals integral a dt, so dv dt equals negative kV over m. And then you just said you didn't want the algebra explained, so you end up with vf equals vie to the negative k over mt. D then asks you to find the total distance, so you take that integral of that last equation that you just you solve for, that VF equation. So you take the integral of VF to find for position, and let's see if we can see it. You end up with S equals VI times M over K. Moving on to number 26, asks you for the diagram first. So all the forces, you have that normal force, and then the force friction, the force of gravity, and the force of tension, which are all there. And then on B, you have the linear acceleration to be determined. So that's just going to be mu Fn equals ma. You are given mu, you're given the normal force, and then the m's cancel, so you end up with 0.5 times 0.4 g equals a. C, then you're asked for the angular acceleration, so angular acceleration is going to equal torque over, oh, that's supposed to be an I, not a T, sorry. That's an I, and so it's going to be equal to the tension of friction plus the actual torque, torque, friction, and then torque of tension. So that's going to be equal to r times mu Fn minus r times 0.6 over the I, which is given as 1/2 mr squared. And then D asks you that to explain why they're not equal. And so if it was not slipping, angular acceleration would equal a over r, but angular acceleration does not equal a over r. So, since that doesn't happen, they're not equal. So, and that's because it slips. It tells you it slips. So it's no good. You don't want a slipping block. Number 28 then was asking you in the first part for the electric potential at point P on the axis. So you just basically made x your distance along the x, and r was constant. So you have to do some geometry and get the square root of x squared plus r squared. So it was just v equals kq over r, aka square root of x squared plus r squared. So B then asks you where the electric potential is greatest. It's right where the radius will be the least, and in this instance it will be where that x is equal to the least number it can be, which is 0, which is right in the center of the ring. So right in the center of the ring, the electric potential will be the greatest. C, the magnitude and direction of the electric field. That again will be an integral. So E is going to end up equaling kq over r, which we determined to be x squared plus r squared. So kq over x squared plus r squared times x over square root of x squared plus r squared. And that's going to be a magnitude of, not a magnitude, but a direction to the right. And then it asks you to sketch a little graph of E as a function of the distance. So it'll be a bit of a decay curve after it passes point X. So yeah, that'll be test number 1977. So that's the one I owe you there. And thanks for a great year, Mr. Keller. Yeah, I learned a lot. So thanks.